Okay. I want to thank the organizers for the invitation to speak. It's a pleasure to be here. I'm going to describe a construction that gives a partial compactification of something called the universal centralizer. And this is an example of a Coulomb branch, so it will fit into the theme of the morning talks. And I'll begin by explaining how to obtain this variety and explaining how it's naturally a symplectic variety. And then I'll try to kind of modify this construction to my purpose. So for today, G will be a semisimple connected algebraic group over C. And I'll require it to be of adjoint type. So it'll have trivial center. And then I'll denote by factor G its Lie algebra. And I'll fix, for the rest of the talk, a principal SL2 triple. So this is a triple of elements that generate a copy of SL2 inside G and that are all regular. And I'll denote my centralizers by superscripts. So the centralizer of the nilpotent E is going to consist of the group elements fixed by the adjoint action. And the same notation will carry over to the Lie algebra side. And then once I have the centralizer, what I obtain is a principal slice. Which is the affine space given by the sum of the principal nilpotent F with the centralizer of the opposite principal nilpotent. And it's well known that this affine slice gives well, it parametrizes the regular conjugacy classes on the Lie algebra of G in the sense that it intersects each regular conjugacy class exactly once and transversally. So it gives a section to the adjoint quotient. And then the definition is that the universal centralizer associated to this group is the variety of pairs G in the group and C in the slice with the property that G centralizes C. So this is like the family of centralizers of regular elements parametrized by their conjugacy classes. And this variety has a natural symplectic structure that is obtained through a construction that's normally attributed to Constant, I think. So call the construction Constant Whittaker reduction. And this is going to be a Hamiltonian reduction from the cotangent bundle of G. So I'll fix a couple more items of notation. B is going to be the unique Borel whose Lie algebra contains the principal nilpotent E. And N is going to be its unipotent radical. And for any subgroup, I'll denote by the corresponding fractor letter the Lie algebra. But I'll try not to write below this line. So then the construction goes like this. We have a Hamiltonian action of this unipotent radical on both sides of the cotangent bundle of the group G. And this cotangent bundle, well, this action produces a moment map, which I'll call nu, to the dual of the Lie algebra of n. And I can understand this action explicitly in the following way. So I identify the cotangent bundle of G with the product of the group G and its Lie algebra via left trivialization and the killing form. And I identify n star with the quotient of G by the subalgebra B, also via the killing form. And then the moment map nu factors through the moment map for the G cross G action. And this moment map is given explicitly in the following way. It takes a pair of an element G in the group and Xi in the Lie algebra to G applied to Xi, comma Xi. So this means that its image consists of conjugate pairs in G cross G. And the fiber over a diagonal point is precisely the centralizer of the corresponding Lie algebra element. And now what we do is we consider in n star, which I've identified with G mod B, the diagonal coset of this principal nilpotent F. And this is fixed by the action of n cross n, because you can imagine that this is like a lower triangular matrix with ones on the subdiagonal, and acting by n pushes it up, but then anything that we've pushed up is killed by the B quotient. And in fact, it's a regular value of the moment map. So this is n cross n fixed. And and the two-sided action of n on the fiber above this coset is free, which tells us, because we're in the symplectic setting, that this is a regular value. And then if I look at this fiber explicitly, it just consists of pairs of points G and Xi with the property that both Xi and its translation by G live in the space F plus B. And F plus B is known to be isomorphic to n cross the principal slice. So this is an isomorphism given by the action map. So this means that when I quotient this fiber by the action of n cross n, I get exactly the universal centralizer. So this makes Z into a smooth, symplectic affine variety. And so we think of Z as a family of centralizers of regular elements that are indexed by by points in the principal slice. And then the goal is to find some kind of partial compactification of Z along the fibers, and to say what happens to the symplectic structure that comes from this reduction when we try to extend it to the boundary of this partial compactification. So the plan is to compactify the centralizer fibers. And the place where they're going to be compactified is inside the wonderful compactification of G. So I'll give a brief description of what this is before I explain how to perform this construction. So I'm going to let G tilde be the simply connected cover of G. And I'm going to let lambda be a regular dominant weight of G tilde with respect to some choice of maximal torus and Borel. And this corresponds to a regular irreducible representation of G tilde, which I'll call V. And then the wonderful compactification of G we obtain in the following way. We have the representation map going from G tilde to non-zero endomorphisms of V. And quotienting by the center on the left produces the group G. And quotienting by scalars on the right gives us a projectivization of this endomorphism space. And because the group G was of adjoint type, and because the weight I chose was regular, this is going to descend to an embedding of the group G into this projectivized endomorphism space. And then the definition is that the wonderful compactification of G is precisely the closure of the image of this embedding. So this compactification has many remarkable properties. And the first is that it's independent of the choice of regular dominant weight that we made. It's a smooth projective variety with a two-sided action of the group G that is extending left and right multiplication on the group itself. Obviously, G sits inside G bar as an open dense subset, and the boundary is a normal crossing divisor. And the action of the group on this boundary breaks it down into a collection of finitely many G cross G orbits. And these are indexed by subsets of the simple roots in the sense that, that the closure of the orbit, so I should say maybe this divisor is a union of rank many irreducible components. And then the closure of the orbit indexed by the subset I is just the partial intersection, the corresponding divisor components. So in particular, this tells us that the orbit closures are smooth. And maybe I will say one more thing about them. So these orbit closures have a very nice geometric description, which goes something like this. So for a fixed subset I have a corresponding pair of parabolics, pi and pi minus, and a Levy subgroup, which is their intersection. And then the closure of the ith orbit fibers over the corresponding product of partial flag varieties. And this fiber is another wonderful compactification of a semi-simple group of strictly smaller rank, which is the group given by the adjoint form of this Levy. So this is a smaller wonderful compactification. And in particular, this means that there's a unique closed orbit of minimal dimension, and it's isomorphic to a product of two copies of the flag variety. So in particular, unique closed orbit of minimal dimension corresponds to taking I to be the entire set of simple roots. And that produces a product G mod B cross G mod B minus. So I'll give one very simple example before we move on. In the case where G is PGL2, and then its simply connected cover is SL2. And here all non-zero weights are regular, so I can choose the representation V to just be the standard representation. And then the map chi is the embedding of PGL2 into projectivized 2x2 matrices. And its image just consists of the matrices with non-zero determinant. So when we take the closure of this image, the wonderful compactification of PGL2, the entire space of projectivized matrices, which is a copy of P3. And inside it, the boundary sits as the 2x2 matrices with determinant 0. And via the Segre embedding, this is just a product of two copies of P1. And P1 is the flag variety of SL2. So this realizes this orbit classification in this very simple example. And I'll give a non-example that says this construction doesn't generalize. So when G is PGLN for n greater than or equal to 3, the standard representation is given by a dominant weight, so it's no longer regular, by a fundamental weight, I mean. So it's no longer regular, and in general, the compactification of PGLN is not just an n squared minus 1 dimensional projective space. It's some more complicated, smooth projective variety. I'm open to questions. And I should say, this is good to give references, that this compactification was introduced by De Concini and Perchesi in the much more general setting of symmetric spaces. So the construction that I gave is a simplified version of their original construction.
Somehow the point is that for PGL2 this works because you just have one root, right? One
yes.
Root. So you just have you have matrices and you add the divisor to infinity, but in general you need many divisors.
Yes, exactly. Exactly.
Did you say anything about the Poisson structure yet? I guess these are also the symplectically of, say,
I'm not going to say anything about so there's a Poisson structure on the wonderful compactification, which is not related to what I'm doing. But I am about to say what the log cotangent bundle is, and then there will be Poisson stuff. Okay. So I said that that the goal was to compactify the centralizer fibers of the universal centralizer inside G bar. And the way I want to do this is by another Hamiltonian reduction, but from a kind of enlargement of the cotangent bundle of G. And the correct enlargement to consider for the wonderful compactification is something called the logarithmic cotangent bundle of G bar. So so I'll denote this by T star G bar D. So this is the vector bundle associated to the locally free sheaf whose sections are logarithmic differential forms. And they're allowed to have holes along the boundary divisor. So if I have coordinates x1 through xn on the wonderful compactification, so that the divisor is given by the vanishing of the product of the first k, then these sections locally are generated by dx1 over x1 through dxk over xk, and then dxk plus 1 to dxn. And of course, when I restrict this log cotangent bundle to the copy of the group G that's living inside the wonderful compactification G bar, I just get the usual cotangent bundle of G. Okay, and the essential observation is that this log cotangent bundle has a canonical log-symplectic Poisson structure. So a log-symplectic structure is a type of non-degenerate Poisson structure, so it's going to have an open dense symplectic leaf, and in this case, this is going to be exactly the cotangent bundle of G. And it's from this Poisson variety that that we're going to perform a sort of analog of constant Whittaker reduction to compactify the universal centralizer Z. So let me say very quickly that there's a good explicit way of thinking about this log cotangent bundle, which is the following. So we can view this bundle as a subbundle of the trivial G cross G bundle on the wonderful compactification in the following sense. So at a point x in G bar, I'll denote by O the G cross G orbit of x. And then I have an action of the stabilizer of x on the normal space to this orbit. Like this. And I have something called the isotropy Lie subalgebra at x, which is just the Lie algebra of the kernel of this action. And this is exactly the fiber of the logarithmic cotangent bundle at x. And it's a subalgebra of this trivial G cross G. And it's a subalgebra of G cross G. And this is how we view this log cotangent bundle as a subbundle of this trivial bundle. So there's actually a sort of alternative construction of the wonderful compactification where we embed the group G into the Grassmannian of group dimensional subspaces of G cross G, and then G bar is the closure of the image of this embedding. And well, I should say maybe we do this by mapping a group element to the corresponding translation of the diagonal subalgebra. And then this log cotangent bundle is nothing but the restriction to G bar of the tautological bundle on the Grassmannian. Okay. So now I run the same constant Whittaker reduction on the log cotangent bundle of G bar. So this means I have my two-sided action of the unipotent subgroup N. And this action is Hamiltonian with respect to this log-symplectic Poisson structure. And it has a compactified moment map, which I'll call nu bar. And again, I can understand it by identifying n star with G mod B. In which case, this moment map factors through the moment map for the G cross G action. Which is now just projection onto the fibers. And this compactified G cross G moment map is exactly, well, both of these moment maps are extending our moment maps for the cotangent bundle of the group G. And in fact, we can see, if you remember, the image of mu consisted of conjugate pairs in G cross G, but now mu bar is a proper map, and its image consists of pairs of elements in the Lie algebra that lie in the same orbit closure. And if C is a regular element, then the fiber above the corresponding diagonal point is exactly the closure of the corresponding centralizer inside the wonderful compactification. So now the theorem well, the theorem is that we consider again the diagonal coset corresponding to the principal nilpotent F. And this point is still fixed by n cross n. It's still a regular value of the compactified moment map nu bar. And there's an isomorphism between the quotient of the fiber above this point by the n cross n action and the variety of pairs xc in the wonderful compactification across the principal slice with the property that x lies in the closure of the centralizer of xc. And this thing on the right-hand side I'll denote by z bar. And you can see that it's a partial compactification of the universal centralizer z in the g direction. So in particular, this partial compactification is smooth, and it has a natural log-symplectic structure that is extending the symplectic structure on the universal centralizer Z, which is the open-dense symplectic leaf. Okay. So now I want to next take a bit of time to describe what these compactified centralizers look like. So let's fix the following space. It's going to be an affine subspace of the Lie algebra that consists of the Borel plus the negative simple root spaces. So here alpha 1 through alpha L are the simple roots. And then for every element x and g, we have an associated object called a Hessenberg variety, which consists of cosets in the flag variety associated to group elements G with the property that G inverse applied to X is contained in H. So this is a definition. And maybe first I say theorem, which is that there is G upper X. Well, maybe what I want to say is fix a regular element C in the Lie algebra. Then there's G C equivariant isomorphism between the compactification of G C in G bar and the Hessenberg variety associated to C in G mod B. So explicitly, now what do these centralizers look like? Maybe more explicitly. When I choose a regular semisimple element, then, well, its centralizer is the maximal torus. So I expect its closure in G bar to be some kind of projective toric variety. And these are described combinatorially by fans, and the fan corresponding to this one is exactly the fan of Weil chambers. And then on the other hand, if I pick a regular nilpotent, then, well, its centralizer is now a unipotent abelian subgroup of the same dimension as the rank of G. And through this identification, the compactification of the centralizer is isomorphic to something called the Peterson variety, which is these projective toric varieties are smooth, but the Peterson variety is fairly singular and in high ranks not normal. And then in the intermediate case, so when X is an arbitrary regular element, these, well, I can write its Jordan decomposition. And then this is reflected in the in the structure of the compactified centralizer in the following way. So I take the reductive subgroup, which is the centralizer of the semisimple part. I look at the corresponding adjoint group, in which the image of this nilpotent becomes regular. And then the compactification of the centralizer of X surjects onto the corresponding, let me denote Peterson varieties by subscripts, onto the corresponding Peterson variety of this semisimple group. And the general fiber is a toric variety that corresponds to the compactification of the center of this levy. So what this means is that I can view this partial compactification of the universal centralizer as a subvariety of the flag variety cross the principal slice, whose fibers are Hessenberg varieties. So this is a smooth family of Hessenberg varieties with a log-symplectic structure. And in this way, I can put on it a C star action that is going to let me decompose it into affine spaces. So remember that we fixed triple EHF. And the regular semisimple element H gives me a map from C star into the group G that just takes T to exponential of TH. And now I can define a C star action on Z bar that has T acting on an element Borel B bar comma C by the usual action in the first coordinate and by a scaled action by T star in the second coordinate. So if you think about what's happening in the principal slice, when I act by gamma of T, this action is fixing F. Because when H acts on F, it acts with eigenvalue -2, but then this is canceled by this power of T. So this is an action that contracts the principal slice to the principal nilpotent F, and it contracts the universal centralizer, or the partial compactification of the universal centralizer to the C star fixed points in the fiber above F, which which is to say the C star fixed points in the corresponding Hessenberg variety.
So you meant T to the H, and you said X plus TH.
When I said
X plus TH, you meant T to the H. T is already in the C star.
Maybe I meant this. Or no.
I think you meant T to the H.
Yeah. Yes. Okay. Right. So these C star fixed points are well known in the Peterson variety, and they correspond exactly to translations of the fixed positive Borel by file group element that is the longest word of some parabolic file group. So these are indexed by subsets I of the simple roots. And then we get a decomposition of Z bar into attracting sets for the C star action. Where the attracting set xi is the collection of pairs where I let T go to 0, is the collection of pairs that flow to the fixed point indexed by the subset I. And such a thing has dimension 2L minus the cardinality of the subset. So what we get is a stratification of Z bar by these affine spaces and a basis for its singular cohomology where each xi lives in degree 4L minus twice the rank of I. So maybe I stop.